Hello and welcome to today's webinar presented by Delubal Software. Today we'll be working in our Structural Analysis and Design program, RFEM 6. The topic for today's presentation is CSA S157-17, reaffirmed in 2022, Aluminum Design in RFEM 6. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the U.S. office and also a sales engineer, and I'm located in Philadelphia, Pennsylvania. My colleagues Alex Bacon and Siska Cho will be your moderators, answering any questions you may have. They're both support engineers, also located in our Philadelphia office. We always want to encourage everyone to ask questions throughout the presentation today. You can do so within the GoToWebinar dialog box as shown here. If by chance we don't get to all your questions, we'll certainly send you a follow-up email afterwards. Regarding the content over the next hour today, I do want to begin in our standalone program, RSECTION, where we'll import in a DXF file to calculate the cross-section properties of a custom extrusion, shown over here on the right-hand side. We'll then integrate this member into RFEM 6. So this is where we will show the modeling workflow of our aluminum carport structure today. We'll talk a little bit about the loading, including also integrating our other standalone program, RWin3, for the CFD wind loads. We'll input information specific to the CSA design for our members. And finally, we'll run our calculation and review the analysis results in RFEM 6, but also the design results according to the CSA standard utilizing the aluminum design add-on within RFEM itself. We'll talk a little bit today about unique capabilities, referring directly to the CSA S157 that somewhat sets RFEM apart from other software out there. So as mentioned, we do want to begin first in our standalone program, RSECTION. And before we get into our example today, I want to talk about a couple different calculation methods available. So within RSECTION, we have the ability to set the thin-walled analysis calculation type, and this, of course, should be used for thin-walled cross-section. So we're talking aluminum, steel, cold-formed steel, and so on. You can see the section over here on the right-hand side would be applicable to this thin-walled analysis calculation, where the stress and force flow is along the element length, but not necessarily the width. Now, with this calculation type, it does require the generation of what we call elements. This will make more sense once we get into the example. But the advantage here of these elements is that once we bring this cross-section into RFEM, we can do the full member design, but we also can generate what we call the sub-panels, which will be taken into consideration with the local buckling checks according to that CSA standard. Now, when we move into more complex sections or sections that deviate greatly in shape from the generated elements, this is typically where we like to move to an FEA method instead. So that brings us to our second calculation type available, the finite element analysis. Now, this is typically used for massive cross sections like concrete or timber, but you can see that it could be applicable for very complex aluminum extrusions as well, like the one shown over here on the right-hand side. This is where the finite element calculation method is applied, and the stress and force flow is along the element length, but also the width. Now, unlike the thin-walled analysis, it's possible to generate the elements, but it's not necessarily required. If we do take that extra step to generate the elements, again, we can carry out those local buckling checks once we are within RFEM. I will mention that we are just briefly touching on this program today. I've linked here a previously recorded webinar that's devoted entirely to RSECTION that will explain these concepts in a little bit more detail. So for today, we will jump to our section here to begin our first cross-section extrusion. Again, we want to calculate the cross-section properties here within the standalone program. We will set the analysis method according to the thin-walled analysis. And I've already taken the liberty to import in a DXF file. This is very easy. Under File, Import, we can go ahead and select the DXF file. Once that's brought in, we see a series of line and node elements. But we need to take a couple additional steps here in order to calculate these cross-section properties. And we're going to begin with first what's called the part. So I can right-click within my navigator to create a new part by selecting the boundary lines. Now, before I do need to assign a new material to this part. So we open up our material database, and over on the left, we have our filters where we can set this to Canada, we can select the material type to aluminum, and we have implemented all materials according to the CSA S157. We see this as we scroll through these different options, including the submaterials on the right. And for today's example, we will choose 6061T6 for extrusions. So once this material is implemented here, we are going to select the boundary lines. So I can graphically select all lines within this model, but I do need to zoom in here, hold down my shift key and deselect these openings. We'll get into the openings in just a minute. So I'm going to do the same thing by holding down my shift key and selecting here all of my elements within the bottom opening. I click OK, and we see this part generated. Now, of course, we need to go back in and add those openings. So we'll go ahead and do so by right-clicking over in our navigator to create a new opening. And I'm going to select here the boundary lines of my first opening, which will be this smaller one up here at the top. Once I click OK, I have the ability here to click Apply and Next. This is nice because the opening is generated in the background, but I'm still within this dialog box so that now I can select the boundary lines for my second opening. I'll go ahead and use my selection box here to select all of these line elements. I click OK, and now that second opening is generated. So again, because we are running according to the thin-walled analysis, we also need to create what's called the elements. And we will get a calculation error if we do not create those. So instead of right-clicking and creating an element here, we have some nice tools down at the bottom. So for example, I can create the element by clicking on parallel lines in the model. And before I do that, I'm going to go ahead and hide the visibility of both the parts and the openings. So they still exist, but they're just not shown here graphically. I'll go ahead and use this tool down here at the bottom where I can select two parallel lines. We see that element generated at the bottom, at the left, at the right, and then also we're going to do it one more time here up at the top. I can right click to exit, but we do need to clean up these elements a little bit further. The elements themselves need to connect here at these center points. So what I'm going to do is to hold down my control key to select both of these center points. Now I want to use the move copy tool. I'm not going to make any copies, but rather I'm going to select my displacement vector here. And this will allow me to choose 2 points, including the center point on the left and the center point down at the bottom. Now I am going to go ahead and zero out the Y displacement so that we're only moving these elements vertically, and I click OK. So now I have the ability here to grab the center point of my bottom element and snap it to the center point of the side elements. Okay, so now that those elements are connected, we need to do the exact same thing up here at the top. I'll go ahead and hit Control to select both of these center node points. I'm going to use my Move Copy tool. We're not making any copies, rather we're selecting the 2 points for a displacement vector. I'm going to zero out the Y displacement once again, so we're only moving those elements vertically. And then I have the luxury here once again to grab onto the center node, snap to the center point of my sidewall elements, and then all of those elements are connected. So you can see here I have a small mistake for this element down here at the bottom. No problem, we'll go ahead and grab this. We'll choose the displacement vector once again, and I'll go ahead and move it down to the center point here, but zero out the Y displacement. So now that those elements have been generated, we're ready to run our calculation. Now, we could continue to add elements in the upper part of this section, but maybe I'm not so concerned with the local buckling checks here. I'd rather just take into consideration the larger tube portion of this cross-section itself. So therefore, if we go to calculate all, we'll see those cross-section properties given to us directly within the table. So it may look like the cross-section properties are based only on the elements, but remember, we do have that part generated. And the cross-section properties such as the area, the moment of inertia, these are all based on the part directly. It's not until we get to information such as the shear area that this is only based on the elements themselves. So again, if you want to consider additional shear area in the upper part, we would need to apply additional elements there. Once we have run this calculation, we want to ensure that we save the results with this file to our computer. We certainly have to have the cross-section properties calculated and saved in order to bring this into RFEM. So everything looks good here, and we're now ready to move on to RFEM directly. So when we create a new model in RFEM, I want to explain within the base data dialog box the second tab for all of the available add-ons. And for those of you joining us today not familiar with the concept of RFEM 6 and the add-ons, the base program RFEM provides a full static analysis. We have access to cross-sections, to materials, not only from the CSA standard for aluminum, but all other cross-sections and materials that we offer from the available standards. It also can integrate with BIM software, but as soon as we have run this static calculation and we want to take this a step further, this is going to require the additional add-ons to carry out the design. So at a minimum, for today's example, we do need to activate the aluminum design add-on to carry out the design checks according to the CSA standard. You'll also notice that I have wind simulation. So this is because I do want to integrate my model with our other standalone program, RWind3. It's certainly not required, but we'll see the advantages of connecting that to our CFD wind analysis program today. Under the third tab, we can generate all of the load combinations automatically according to the NBC standard. We see the other international standards like ASCE 7 also listed here. Under the aluminum design add-on, this is where we have now added the new CSA S157 standard, but you also have access to the ADM code and other international standards that we do offer. So now that this information is set, we're brought into the main program RFEM here, and you'll notice that the interface does look very similar to what we saw within our section. I have already added a couple sections with materials defined in this model, so let's quickly review that. Under the cross sections, we can create a new cross section here within our cross section library. So in the upper left, we have access to all the standardized cross sections like from the ADM or the CSA S16 or so on. What's interesting about the CSA S157 is that there are no cross sections affiliated specifically with this standard. So most likely you're going to utilize these thin-walled sections here. And that's exactly what I did for this first cross section. I went ahead and chose an I section. So once that is selected, we would assign a material to it. Again, this looks identical to what we saw in our section where we use our filters and we can select a 6061 material here. Under the second tab, this is where we define the dimensions of the cross-section directly. And the program will go ahead and calculate the cross-section values for me here under this third tab. Now, we also have our R section cross-section that we brought in from our separate program. This is imported in here from this option within the library where we can directly link to the save file within our Delubal Center. So I went ahead and brought this in. The material was already assigned, but we could reassign this material if we'd like. And notice we have the subpanels tab. So again, this is the generation of those elements that we created where the program knows the length, the thickness, therefore the length to thickness ratios, and knows that these elements are supported either on both sides or one side. And this is the information that is further used in the aluminum design add-on to carry out local buckling checks for, again, these custom extrusions. So we are now ready to begin modeling our columns. You'll also notice that I placed a few nodes here already. You can easily create a new node with our quick tools up here at the top, or notice in table format, we can activate here the basic objects and the nodes tab and input in the coordinates directly here. So we'll begin by drawing a new member, and within the member drop-down options, I'm going to choose the perpendicular to work plane. So this is nice that it will just automatically orient my column perpendicular to the work plane that I have already displayed here. The member type is going to be a beam with the cross section defined here, that I section. The program by default will set everything to fully fixed. It's not until I come in here and add a hinge activation, do I get a new tab? Could we apply something like a moment release? And that's what I'll do for this first column. At the member end, I want to create a new hinge definition. And you can see the program automatically defaults to releasing the moment about the member's local Z and Y axes. I'll go ahead and just release that for the local Y. We can also consider partial fixity with spring constants, or keep in mind that RFEM is a nonlinear analysis program. So if we want to get pretty detailed with these member hinges, we have these additional nonlinear options here. We'll go ahead and leave the member hinge applied only to the member end. I click OK, and I just need to specify here the height of the column of 3.54 meters, and I'll go ahead and snap to the origin point. My second column is going to be 2.2 meters, and I'm going to snap to my node at the left here. So I can right click to exit out of this dialog box. Now you'll notice a couple color coding here on both of those columns. This is what we call member representatives. We're not using those today, so we'll go ahead and turn them off within our navigator options. The next step is to draw a beam, but this time we're going to choose the simple option where I can just simply snap from one node to the other. Same cross section applied here and material, but this one I want to be fully fixed. So I click OK, and I'm going to snap from my node to the left and the node on the right. And so now we see that beam spanning between the two columns. I'll right click once again, and I'm going to take this beam, and under the members option, when I right click, I have the ability to divide the member by a set number of intermediate nodes. So we'll go ahead and divide this by 6 intermediate nodes. Now you do have the option to essentially create these on member nodes without dividing up the member into segments. But for today, I am going to let the program go ahead and divide these up. So notice these are separate segments here. I'm even going to take this a step further to use my tool up here at the top to break apart the beam member where the column frames in. Now, it's not necessarily a detrimental thing that we have broken these up into separate segments, because what we have the ability to do here is to select all of these separate segments that make up this continuous beam. We can right click, and under the members option, we have the ability to create what we call a member set. So this member set detects that these are continuous elements here, and we can actually design this as one continuous member once we get into the aluminum design add-on. We'll go ahead and turn off the member set representatives here for my member sets as well, just visually. And the final thing I want to do with this frame is to draw in a couple additional columns here at an angle. So we will once again select the member drawing option here for simple, where I can just snap between two nodes. This one will be the same I-beam, but I do want to activate here the hinges. I'm sure the correct section is selected here within my dropdown. And I do want to apply that moment release. And because I've already defined it once in the model, I don't need to keep redefining it. I simply select it here from my dropdown. I click OK, and then this is going to allow me to snap between the base of my existing columns up here to my beam. I'll right click to exit out of there, and that's all that will entail this first frame. So I'm going to use my selection box here to highlight all elements, but you'll notice I am not selecting the nodes at the base of the structure, and there's a reason for this. Furthermore, I'm going to hit the Shift key on my keyboard to deselect the nodes at the top of the column, and there is a reason for this that we'll see in just a minute. So I'm going to use my Move Copy tool, where I am going to create one copy. The displacement vector is going to be in the global y direction of 3.86 meters. Well, under the second tab, we have the ability to activate what we call step links. So I'm going to turn this on, and we get a new tab here where I have the ability to create members between copied nodes. I can create a new definition type here for this member, and I'm going to deactivate the hinges. I want this to be fully fixed, but this is where I'm now going to select that R section, that custom extrusion that I brought in for this particular member. I click OK. I click OK once again, and now what you'll see here is that the program has automatically generated these purlin members between those copied nodes. So this is why I was careful to not select all nodes, but rather just the ones where I wanted those purlins to exist. Now I'm going to highlight all of these members here, and let me create a quick visibility, and we'll kind of go to a fully rendered section. When I zoom in here, you'll notice that you do get a nice rendered view of this custom extrusion. So we can ensure that it's oriented properly, even though it is a custom section brought in outside of RFEM 6. What else I would like to do with this member is if I right click while all of these elements are selected under the members tab, I have the ability to extend these members. I'd like a slight overhang over those I-beams. And we can specify here an offset on both sides of the member of 0.32 meters. Now I want to create new members here rather than extending the existing member. So when I click OK, what you'll notice now is I have these slight overhangs here. Yes, they are separate elements, but just like what we saw with our larger spanning beams here, I can select all of these elements. And even though they're 3 separate sections, I can right click here and once again create what we call the member set. So under the members, we can create the member set. The program detects the continuous elements here. It creates separate member sets for each one of these. And now we can design these as one continuous member, again, for the aluminum design. I'd like to make some additional modifications here, including adding an eccentricity to shift these members up above my I-beam. But before I do, what I'm going to go ahead and draw is a new surface element. So I'll turn this into wireframe view, and maybe we have some type of sheathing on top of this carport for protection. We can actually model that in RFEM as a surface element with the option polygon. But the surface type is special in the sense that I want it to transfer loads only. I do not want it to add stiffness to the structure. So therefore, we choose the stiffness type load transfer. Notice we don't select a thickness. We don't apply a material because we aren't accounting for the stiffness of the surface itself, but rather this is used for either one-way or two-way area load distribution to distribute these loads directly to the purlin members. And in this case, I'm going to use distribution based on the surface's local y-axis only. I can click OK, and then I have the ability to select the 4 corner points of this surface, and I'll go ahead and close the loop here with my 5th click. We can right click to exit. Now we see the display of the surface cells. Again, we're not using that for today's example, so under special objects here, we can go ahead and deactivate that graphically. So looking at the rendered view, we see that surface element applied here. Now, what I need to do here is to select all of these particular members. And in order to apply the eccentricity, I'm going to go ahead and right click here, and under members, we can edit. There is an additional option within the member dialog box here to apply an eccentricity. And under the eccentricity tab that pops up, we create a new member eccentricity definition. Now, what's nice is I don't have to manually define this eccentricity. Rather, I can tell the program to take the bottommost point of these custom extrusions, these purlins, and offset it from another object. And in this case, we will choose a member. So I'll need to cancel out my visibility mode here, and I'm going to select just one of the member segments of my I-beam. And I want it to be offset from the uppermost point of that particular cross section. I click OK, and now we have this definition type to apply to the member start and the member end, and I click OK. So what you'll notice now is that the members have been shifted on top of that I-beam accordingly. The final thing to do is that if we look at these members, you'll notice that they are essentially oriented in the vertical direction here based on the global z-axis. Instead, I want them to be perpendicular to the slope of my carport. So we'll make one final change here by going to the cross sections, for example, and I can just quickly select our section. Notice everything is highlighted accordingly. And I also notice a small mistake here. Let us go ahead and fix this eccentricity. Looks like it was forgotten. So we applied the eccentricity. We've already defined it here. So we'll go ahead and select it from this dropdown. So now that all of these members have the eccentricity, again, I want to highlight them to slightly rotate them. So I can right click and under the members dialog box, once again, you should be pretty familiar with this dialog box by now. Under the cross section, we can rotate the cross section itself, but even more so, we can specify a rotation based on an object within the model, such as the surface. So we only have one surface defined here, surface number 1. And notice when I click OK, what ends up happening here is that these members are shifted ever so slightly. So now we see them perpendicular to our roof slope here. So everything looks good in terms of our member modeling. We will apply some quick supports down here to the bottom. So we will select here a new nodal support up in our quick tools. There are some default options. Of course, you can create your own definition here, but we'll choose the standard pinned or hinge support. I click OK, and I'll go ahead and select all of my nodes at the bottom. The final step within our modeling process is something that I'm actually going to jump back to the PowerPoint to explain further. So this is one of these unique capabilities that RFEM has the ability to consider. When we refer to the CSA S157, the design of members for shear, there is the ability to consider stiffeners. So the first clause, 12.1.2, is the design of the flat webs without stiffeners. So this is for flat rectangular webs with boundary flanges, but no stiffeners defined. Therefore, the factored shear capacity, V sub R, is given with the equation here. Alternatively, clause 12.1.3 has a design of flat webs with stiffeners. So this is flat rectangular webs, once again with boundary flanges, where stiffeners are defined because the web buckles before yielding. Therefore, our factored shear capacity, V sub R, is the lesser of the two equations shown here. So certainly different than the previous equation in clause 12.1.2. We can actually design to consider these stiffeners in RFEM, and we do so by applying what we call the member transverse stiffeners directly to these elements. Now, this is limited in the current state to I-beams only. So only I-beams can have these type of stiffeners, but for our example today, this is certainly applicable. And you can see the dialog box shown here where we can consider the stiffener input, which is what we'll go ahead and go back to RFEM and do now. So under the types for members folder, as you can see over on the left, we have member transverse stiffener. So I double click to create a new definition type here. The first thing I want to do is to select the member sets. And the member sets, we can select, there's a faint dotted line grouping together all of these separate segments. We don't want to select the individual member segments, but rather this set of members. So set of members number 1, and we can select set of members number 2. So once I click OK, I specify here the stiffener type, which will just be a flat plate. And the thickness is automatically defaulted here to 5 millimeters. So we'll go ahead and keep that for our example today. I do need to specify the distance where my first stiffener will be placed from the member end. I cannot put in here a value of 0. I will get an error. I need to, at a minimum, specify half the thickness of the stiffener itself. So this will be 0.0025 meters. We will have multiple stiffeners along the member length. So we'll specify 8 stiffeners with an offset distance here of 1.142 meters. We can also toggle the view here in our display so that we can see these stiffeners applied to the member along the length within the dialog box directly. But once we click OK, these stiffeners are also applied graphically here. So notice I placed a stiffener at every location where that purlin member is framing in above it. Now, the stiffeners do not affect the analysis. We're not going to see internal forces, deflections change because of the stiffener. It is only considered once we move into the design within the aluminum design add-on itself. All right, so the modeling workflow is complete. We now want to move in some of the move to some of the input options specific to the aluminum design add-on. So for this, I am going to go ahead and pull up an already saved model here where a lot of this information is already input. So we'll begin with first our columns. So very simple example, highlighting all my columns. I can double click and we're once again brought into our member dialog box option here. Notice there's a design properties checkbox. This is telling the program that not only do I want to carry out the analysis within RFEM 6, but I want to take it a step further to carry out the design utilizing the aluminum design add-on. When I uncheck this option, several of the tabs disappear at the top, and this is telling the program I'm only interested in the static analysis. So let us move through a few of these tabs here to explain in a little bit more detail. The first is going to be the effective length input. So we'll take a look at this existing definition type here. This just all relates to unbraced lengths for the stability failure mode. So flexural buckling about the strong axis, the weak axis, torsional buckling, lateral torsional buckling. So we'll go ahead and carry out the design check for all these. Now, if you have a tube type section, so for example, our custom extrusion today, maybe we're not so worried about torsional buckling, lateral torsional buckling, you could completely turn these off as well. The lateral torsional buckling critical moment capacity. This first option is determined by an eigenvalue method. What this means is that we are going to extract out each individual member. In our case today, these were these columns. We're going to run a separate eigenvalue analysis to determine what this critical moment capacity is. So this might be an advantage when we're talking about members that are not in a straight plane, that are part of a member set, or maybe it's a curved member where the code doesn't really address how to calculate lateral torsional buckling capacity. Now, alternatively, if you would like to design directly according to clause 11.3, you can toggle to this option here, and we'll go ahead and refer directly to the code. The second tab, this is all to do with these intermediate supports. So you can see that the program will automatically default to place an intermediate support, member start and the member end. And not to be confused, these supports are not global supports. They're not affecting the analysis, but rather they are used so that the program can determine or detect the unbraced length between these supports so that we can use it for the stability design checks. So you have 4 degrees of freedom at these end nodes: displacement in the strong axis, the weak axis, and then rotation about the member's local X and local Z. It's up to you as the engineer to input in what is restrained versus what is free. And then this information is ultimately used to calculate the effective length within those design checks. Notice that the effective length factor defaults to 1 here, but you could certainly override this. Now, the advantage of using the intermediate supports is that if I come in and I make changes to the geometry of my model, let's say we increase the height of these columns, these intermediate supports follow that geometry and our unbraced length is automatically updated. We don't have to come in here and keep manually updating the unbraced lengths, again, if our geometry changes. So this is a pretty simple example for the first sets of our members here. We'll get into a little bit more complex with some of the other member types in just a minute. We also have the ability to set a local cross-section reduction. So I can create a new definition type here. We create a new reduction type. This is if we have any openings or holes within our section, we could define that here so that our effective net area is decreased. Now, this comes into play when we're talking about tension design checks according to the CSA standard. Again, this does not affect the analysis. This is purely related to the capacity once we do get into the aluminum design add-on itself. Now, we don't have any reductions for our example today, so we'll go ahead and leave this empty. The design configurations. Here is where we have two design configurations, one for the ultimate and one for serviceability. So taking a look quickly at ultimate, really nothing too interesting here. We just have some design ratio limits. If we'd like to ignore some of these design checks, we could increase those limits directly. For the serviceability, this is a little bit more interesting in the sense that this is where we set our limiting deflection ratios for both strong axis deflection checks and weak axis. And notice for both of these, the limiting deflection ratio for our beams are L over 360, so if they're supported on either end. And for cantilevers, it's set at L over 180, but we could certainly come in here and override these values as we see fit. So once this information is input, we then jump to the design supports and deflection. If we do absolutely nothing within this tab, the program is going to assume that this member is supported at both ends. Therefore, it will refer to the simply supported limiting deflection ratio of L over 360. If we have a cantilever, then we would need to come in and define a new design support definition here, either at the member start or the member end. This is the only way that the program knows, okay, I need to refer now to L over 180 for the limiting deflection ratio of a cantilever. But for today, these members are supported at both ends, so we don't need to do anything further here. So we also have to input in all of this information for our member sets. So these are going to be a little bit more complicated up here at the top. And I'll go ahead and double click on this member set. That's our continuous I-beam here spanning across our columns. Now remember that although these are separate segments, as I mentioned before, the advantage of the member set is we can design it as one continuous member. We have the exact same checkbox shown here for design properties with the exact same tabs under the member set itself rather than the individual members. So quickly going to the effective length, let's take a look at this input option. So once again, we have all of the stability failure modes turned on here, but under this second tab, we have many different members framing into this particular element at different locations. So we have the ability to activate here intermediate nodes, and then I can use my selection option here to go back to RFEM, graphically select this member set, and all of these nodes along the member length are automatically detected. But again, it's up to me as the engineer to come in and say, okay, I recognize that I have a column at these locations. So I'll go ahead and restrain that in the strong axis. But at other locations where we only have the purlin framing in the weak axis direction, we'll go ahead and restrain that here. And in some other scenarios, it may be all 3 degrees of freedom, all 4 degrees of freedom, whatever it may be. But now the program will automatically detect the unbraced length between these design supports. Again, if geometry changes, these intermediate supports follow. Unbraced lengths are automatically updated. One more thing to mention too, remember that we have these purlins framing in here at the top of our I-beam. So realistically, this is only braced at the upper flange. We have the ability to set that within the drop down at the bottom with the eccentricity options, either upper flange, lower flange. If we have it set to none, it means it's supported at both flanges. This does affect lateral torsional buckling capacities, so it's important to properly set that, again, if we are only braced at one of the flange versus both of them. Everything else remains the same, except for I want to jump to the design supports and deflection. So I'm going to go ahead in this graphical view here just to turn off the display of those intermediate supports. If you remember that we have this continuous beam and we have columns framing up into this member at 4 different locations. Well, we want the program to apply the relevant limiting deflection ratios at the correct locations along the length of the beam. So for example, at these overhangs, this is a cantilever. So we should refer to L over 180, but between these columns, we would like it to refer to L over 360. The only way to have the program detect this information is to input in those design supports. Otherwise, it assumes that the member start and the member end are the only locations where this member is supported. So you'll notice that I went ahead and I have defined these design supports where the columns frame in at the relevant nodes. And we'll go in here into this design support definition. Now, the general design support is just to be considered with deflection. So we're talking about whether the program should refer to a cantilever versus a simply supported. But you'll notice that I have this set to a special type called aluminum. So for this, let us go back to the PowerPoint once again to talk about the advantage of this. This aluminum design support all relates to the ability of RFEM to design the members for shear, in particular web crippling checks. We refer to clause 12.3a, where we can carry out this web crippling check for flat webs with the factored resistance C sub R equation given directly within this clause itself. Now, there's also the additional clause 12.3b for webs with a bent radii at the corners. You can see the factored resistance C sub R with the modified equation shown here. Well, the web crippling checks can be considered in RFEM. And I think this is something very unique because most design programs are not carrying out web crippling checks. And we do so with that special aluminum design support input that we were just looking at within RFEM. Now, there are some limitations to this. The member must have zero rotation and it can't have an eccentricity defined. So in our case today, unfortunately, those purlin members that we added a slight rotation, we added an eccentricity, are not applicable for these web crippling checks. However, our continuous I-beam can be checked for web crippling. And I went ahead and did so, applied these where we have the column framing into the underside to the bottom flange here of this beam. Maybe, for example, we want to check out web crippling at these locations just as an example. So therefore, let me actually cancel out of this particular, and we'll go back into the original definition type. The support width would need to be defined here, and this is just the width of my column underneath it. So that's what I've input in here. Also specific to aluminum, we need to specify if this is an end support, and if so, we need to input in the eccentricity difference from the end of the beam to the center of the support itself. There's a nice feature in RFEM here where I can use the measure tool and I can simply snap on one node to the end of my beam, and then that distance is automatically input into this particular setting. This is also active for deflection design, so it can be considered for both web crippling and deflection. So once this information is input at the relevant nodes, again, we should see those web crippling checks carried out. Okay, so all of the information specific to the aluminum design add-on for our members is complete. And I also had done so for the purlins. I would highly encourage you to download this example model. It's already available on the web page that you registered for this GoToWebinar. Spend some time looking at the effective length input, the design supports, because again, that will make a little bit more sense probably the more time that you spend with it. So let us turn now to loading. Within this model, I do have 4 load cases already defined, including dead live, snow, and wind. So when we look at the applied loads of dead load, just a simple surface load applied directly to the surface element itself. But remember, this surface has no stiffness, so it should be distributing these loads to the purlin members based on their tributary area. And under the display options for surfaces, we can actually display these loads graphically. So now you can see here the loads applied directly to the members before I run a calculation. Again, based on one-way area load distribution, taking into consideration their tributary area. Same concept here for live load. Also, same concept for snow load. If we go ahead and turn this back off, this is just a projected surface load to account for the snow loads applied to the structure. Now, I will mention that under the Load Wizard folder back in the Navigator, we do have automatic snow and wind load generators according to the NBC standard. So if that's applicable to your structure, you could certainly use that within the program. But for today, we'll go ahead and manually apply that snow load. Now, wind load. This one is going to be a bit unique here in the sense that I am going to take advantage of our CFD wind analysis program, RWind3. So this is a standalone program, but I'm integrating it here with my structure design. And the reason why is when we refer to the NBC clause 41712, the wind loads are given for canopies or maybe considering carports only if they are attached to buildings. And in our case today, we have a freestanding carport. So therefore, the code isn't so clear on exactly what loads we are supposed to apply to our structure. So this very might well be a situation that we use something like CFD wind analysis just to verify our assumptions, our guesses, in addition to referring to the NBC standard for these wind loads. So you can see my wind tunnel generated here. I'll tell you too that we do have previous webinars devoted entirely to our wind. So if you're interested with that, certainly refer to our YouTube channel. But I am going to apply just one particular wind load case here. I did take this also a step further by importing in under File Import an IFC file. And this IFC file is currently hidden, so we'll go ahead and activate that. This is just a car. So I want the wind loads to be to consider this car parked under our structure. Now, this IFC file does not affect the RFEM analysis, the design whatsoever. It's purely just used once we get into our wind, and that will make more sense once we look at our results there. So perhaps we want to look at different scenarios of the wind loads with or without the car, different wind loading directions, and so on. Now, the final thing to do is to take a look at our load cases and combinations. Remember, we are generating these load combinations automatically according to the NBC standard. This means that two design situations are automatically created here. The ultimate limit state design situation, which you can think of this as grouping together all of our factored load combinations that once we get into the design, the aluminum design add-on, we use these load combinations for the ultimate limit state. We also have the serviceability design situation, so our unfactored load combinations that we will eventually use for our deflection checks. Now, I'm going to go into the combination wizard settings here, and I want to refer to the CSA standard clause 8, in particular B, where second order effects are required to be considered, otherwise known as P delta. So by default, all load combinations are run according to a second order analysis. You'll see here a large deformation is also available. This means that both big P delta and little P delta are considered. We don't have to add nodes along the member length for little P delta. This is all considered automatically with the RFEM solver underneath the hood according to this analysis type. So therefore, we are fulfilling Clause 8B's requirements. Looking further at Clause 8D, we need to account for the member stiffness reduction due to inelasticity. And the code requires this tau sub B stiffness reduction factor be applied to the flexural stiffness of our members. So we account for this by turning on a new structure modification. And I'm going to create a definition type here for my members. And under the members definition option, I have a drop down here all the way at the bottom for the CSA S157. When I select this, you can see here that tau sub B will automatically be calculated for the member based on the axial stiffness. We will then apply this reduction factor to the flexural stiffness of the members. It's based on the axial loads applied to the member, which will adjust this tau sub B factor. Now, additionally, Clause 8E says that we must account for uncertainty in stiffness and strength. So, therefore, an additional factor of 0.8 should be applied to flexural, axial, and the shear stiffness of the member. So, we can see that again taken directly from the code and applied here within this definition type. Now, we can apply this to all members, or we could graphically select the members that we would like to reduce the stiffness. For this example, we will apply it to all members. Now, I'm going to take this definition type, I'm going to make a copy, and I'm going to turn off the stiffness reduction for this third definition type. The reason why is that for my factored load combinations for the ultimate limit state design, we want to run according to second order analysis. We want to reduce those stiffnesses. But for serviceability, sure, we probably still want to run according to second order analysis, but we don't typically reduce the stiffnesses for deflection checks. So therefore, I can create or go ahead and select this third option within my dropdown. And the most telling will be to jump to the load combinations tab. Here you can see those factored load combinations in red belonging to that first design situation with the stiffness reduction applied. If I jump down here to my green load combinations, these are unfactored belonging to that second serviceability design situation where the stiffness reduction is turned off. Okay, so now that all of this information is ready, including our modeling, our loading, we are now ready to run the calculation. So I will toggle here to an already saved model. So we'll go ahead and see this pop up here. So let us begin by taking a look at initially first that our wind load case. So if you remember, this was our wind tunnel that we applied. And what I'm going to do is to actually jump into our wind directly. So you do have the ability to run this entire calculation silently in the background without ever leaving RFEM. Alternatively, we can go ahead and look at the RWIN model directly in this standalone program. And you'll see that this carport structure was automatically exported out to this numerical wind tunnel. We also have our IFC file considered here. We have our wind loads generated according to the NBC standard. And once we run the calculation, what we're presented with here is the pressure on these various objects. So as I scroll in and I zoom around at the different options, including my members, but also my surface here, I see those pressures listed, including the suction force on top of my carport structure. We also have pressures on the car element itself if we're interested, but that's not so applicable for our example today. But we can view the wind pressure coefficients. We can take a look at wind pressures in and around the structure with our slicer option shown here, including the velocity or the velocity vectors. And we also have the ability to display the streamlines. So this is probably everyone's most favorite display option. This is going to show the particles as they move through this wind tunnel and how our structure is affected. And even more so, can activate here the flow animation. So this is just going to show the particles moving in and around the wind tunnel. We can also save this as a video file and attach it to our calculation report. So this just kind of takes it a step further, again, beyond the code to double check what these wind pressures are exactly. But once we exit out of our wind and we go back into RFEM, the program converts these to static loads. And this way we can combine with the other load cases within the load combinations themselves, like live load, dead load, snow load, and so on. So now we'll take a look at what the static analysis results look like here within RFEM. So I'll go ahead and turn on the global deformations, and you'll notice I have the ability here to view the deformations on the structure as I kind of move through these different load combinations. And this is important just to ensure that I'm seeing results as I would expect. But we can also view the member internal forces. So our axial loads within our columns are important. Our shear forces, especially for those purlin members. We can view bending moments. Keep in mind too that whether it's a member or a member set, we can always right click to view what we call the results diagram. This is going to allow us to display this internal member information in a little bit more detail, like the internal forces, the deformations. You'll notice here I can switch to different load combinations. I can save this to my printout report. So this should be a pretty complete analysis here for our static results. And finally, we also have the ability here to display the support reactions. So the support reactions are shown here graphically. Now, for any of the static analysis results, everything is also shown in table format. If we jump to the static analysis, for example, we can view the results by member or by node, including these support forces. Notice that the table is synced up here directly to the model. And we can also export this out to Microsoft Excel at the click of a button for further sorting capabilities. So once we have reviewed the static analysis, we want to drop down here to the aluminum design results. So we can make that change either down here in the table or up here in the navigator. And just to quickly take a look at the input data, you can see here that the design situations are set: ultimate limit state and serviceability limit state. And this is what we relate to the limit state types over in our second column here. Now, the objects to design, this is going to be either our members, our member sets, so we can go ahead and take a look at those accordingly as well. So once we have set all of this information here, we run the calculation and we now have the design ratios on the member. And when I'm looking at the available options here, we can view by loading, by cross section, but I'm going to jump to the design ratios by the member set. And you can see here that we'll first review our continuous beam element. So it was designed as one continuous element. We see every single design check available here from the CSA standard. This includes both the ultimate and the serviceability. Now, if I'm only interested in seeing the controlling design ratio, I just use my filters up here and I can select the max. And now for every single member set, I see here the controlling design ratio only. So you'll notice we do have some failing design checks here. If we zoom in, this is actually that small little cantilever portion of our purlin is failing with deflection checks. This is a carport. Maybe we're not so concerned with deflections. We could either turn that off altogether or we could increase the limiting deflection ratio. But nonetheless, it is important to see that it's very clear and transparent which checks are failing versus which ones are passing according to the code. So going back to our member set here, we have these different checks that I had pointed out, and notice that the table is synced up here with that red arrow to kind of show me where that controlling check is. Let's take a look at shear in the Z-axis, where I can launch what we call our design check details. And this is going to show me line by line the code formulas, the references, and ultimately how I have calculated this design ratio. So very, very transparent, the opposite of a black box, and where these design checks are coming from. But if you remember, we had input in those various stiffeners along the member length. Well, this is referred to in clause 12.1.3, where we can actually design the shear to consider those stiffeners directly. We also see here web crippling. If you remember, we applied those design supports where the columns framed in. We could go ahead and activate the design check details here. And you'll notice again, all of the equations, the code references, and carrying out this pretty unique design check for web crippling for these member types with those design supports selected. Uh, the final important thing to show you is if we go to the design ratio by cross section. So remember, we only have two cross sections in this model, our I-beams, and then we also have that custom extrusion shown here. So if I go to the design check details for compression design of my R section member, this is what I want to point out to you here. If you remember way back when in our section, we again defined those elements. Well, those are brought all the way into this add-on, and we can see here each of those elements and if they're under compression, how they're classified. Class 2, Class 3, we can see the effective section also listed here. All of this information is then utilized within these design checks to also account for local buckling. We can also see here under our diagram and section, if you wanted to view the stresses, either for the effective section or the gross section, this is possible. We can view here normal stresses. We can view here shear stresses, von Mises stresses. This is all possible with a quick view of this particular cross section at this X location under the given loading. So that's just a brief overview of the design options within the aluminum design add-on. So that will go ahead and sum up our example today. So we'll go ahead and go back to the PowerPoint to conclude our presentation. So if you liked what you saw with aluminum design and the newly implemented CSA standard, or you're interested in RFEM, RWind, RSECTION for any of the other capabilities, we would love it if you would go ahead and reach out to our sales team here. We could certainly schedule an online demo or just a quick chat to talk about some of the DeLubal products available. Now, the QR code can be used here, but also at the bottom of the screen is our contact information to our Philadelphia office. Our phone number is given, and our email address is info-us@delubal.com. We will have many more upcoming webinars. We try and do these approximately once per month. You can register at delubal.com under support, training, and webinars. As most of you know, I tend to send out a reminder email about a week before these take place, so keep an eye out for that next month. PDH certificates will automatically be emailed to all participants who were here for the full presentation. So that is a requirement of the states that we are pre-approved providers, that you are here for the full 60-minute duration in order to receive that PDH. Now, if you watched with a colleague or you watched in a conference type setting and you yourself did not register with the GoToWebinar platform and you are wanting PDH, you will need to request that at the email address shown here, info-us@delubal.com. So again, if you yourself did not register and you're interested in that PDH, shoot us an email, let us know who you watched it with, ensure you were here for the full duration, and we'll be happy to issue that. Now, PDH is not sent automatically after this webinar ends. It usually takes us about a day to get those together. And with that said, I want to thank everyone for attending. There will be a short survey that pops up. It would be great if you took just a couple minutes to fill that out so we can continually improve our future webinars. And as always, I hope to see you at the next one. Thank you.